So now, after an overnight ethanol precipitation, we have spun our DNA, our precipitated DNA for 20 minutes, and then you're going to pour off the supernatant. Now remember, when you're pouring off the supernatant, you have to commit. You have to make sure that it's all in one clean pour, not the pour, because that will dislodge your pellet. Keeping an eye on the pellet. And we have a very, very tiny, very difficult to see pellet right here. It's very, very small, very, very hard to see. And it's just a small white speck, basically. But actually, that's probably at least a ½ milligram of DNA. So a little goes a long way with DNA. So now we need to ethanol precipitate a second time. To do this, we're going to bring our pellet up in water. So we're starting by bringing it up in ½ ml of water, swirling it around, letting it dissolve. After it dissolves, we're going to put the ½ ml into a tube, and then we're going to add another ½ ml of water to the container, and again, swirl it around. We're trying to make sure that we've got all of the DNA from our container here. And then when we do that, we're going to add 3 molar sodium acetate, a small amount of 3 molar sodium acetate. That's in your protocol. And we're going to add 100%, 200 proof, 100% ethanol to this. Do not ever drink pure 100% ethanol. It will burn your throat as it goes down. I know college students are very fond of getting as much alcohol as they can in their systems, unfortunately, sometimes, but this is not something you ever want to drink. And so after we have added the second 500 mils in here and added it to our tube, put in the 3 molar sodium acetate, put in the 200 proof ethanol, we're going to make sure that we mix, because again, if you don't mix, you're going to have an aqueous layer that will freeze in the freezer. You're going to have an ethanol layer on top. And if you have not mixed them, you will not get DNA precipitation. So we're going to put everything together in our tube, make sure we mix, and then we're going to put it either into a -80 freezer for probably a ½ an hour, or even better, an ethanol dry ice bath. And an ethanol dry ice bath is made by taking around 95% ethanol, or at least 70% ethanol minimum, and putting dry ice in it until it's very, very cold and just is slowly bubbling. When you first put the dry ice in, if you put in too big of a chunk, it will probably overflow your container. We have insulated buckets that we do this in. And so by putting the dry ice in slowly, you're allowing it to cool slowly. So that actually gets colder than -80. So it's a little bit better to increase your precipitation of DNA just a little bit. DNA will precipitate even if you don't put it at this cold temperature, but it will help it, give you an extra couple % of yield. And, you always want to try to maximize your yield whenever doing anything. So we're going to pick up after having put this in our ethanol dry ice bath or -80 freezer for ½ an hour. And then we're going to spin our samples for 20 minutes, and we'll pick up with the video at that point. Now we have pelleted after the second precipitation, the second ethanol precipitation. And again, we are pouring it off and keeping an eye on the pellet. So this is what small pellet right there. You can take a Kim wipe to blot the excess liquid coming off. You can even put the Kim wipe a little bit into the tube to get off any excess ethanol, to avoid having ethanol on your pellet when you bring it up in water. But you don't want to get that Kim wipe anywhere near the pellet, because Kim wipe versus pellet will lose every time. It will suck up your pellet and you will never see it again. So after you've done that, you're going to take a ml of water And you're going to simply add that ml of water and resuspend that pellet by flicking in that ml of water. Once it's resuspended, then you're going to dilute it appropriately and read the concentration on the spectrophotometer. After you finish precipitating your DNA in the tube, you're going to add TE buffer to resuspend the DNA. For this protocol, you're going to add 1 mil of TE buffer, and TE buffer is 10 millimolar tris, 1 millimolar EDTA. It just keeps the pH constant, and it chelates those divalent cations to keep your DNA intact. But remember, you want to freeze your DNA if you're trying to store it long term. You never try to keep DNA in liquid form long term, because you will get some degradation of the DNA. So after you have brought up your DNA in 1 mil of the TE buffer, you're going to be diluting it. Now, not everybody at this point has to bring up their the DNA in 1 mil of buffer. When I was working in a lab, our preferred dilution, we would bring it up in 0.5 mils of buffer. So as long as you know the volume that you're bringing it up in, you're fine for the next step. So then you're going to do a dilution of your DNA, because if you tried to add it straight into the spectrophotometer, it would overwhelm and it would be out of the absorbance range of the spectrophotometer. So you're going to take 975 microliters of water and 25 microliters of DNA, which is a dilution factor of 40, and you're going to read the absorbance at 4 different wavelengths. You're going to read the absorbance at 320, 280, 260, and 230. 320 measures undissolved particles. If you have any dirt in there, your absorbance at 320 should be fairly low, below approximately 0.1. You're measuring it at 230, you're going to measure organics in the solution. Now, remember, you have brought it up in TE buffer with and so you're going to have some organic absorbance in there. But if it's too high, this can indicate you have some ethanol left, or maybe you didn't take out all of your isoamyl alcohol from the DNA and you still have some remnants of that. So as long as your absorbance is less than approximately 0.3, with that, you're probably in a fine range. If it's higher than that, maybe you'd want to try reprecipitating your DNA to remove any organic contamination. But you would expect to see some absorbance in there. Now you're also measuring it, as I said, at 280 and 260. Proteins, as we have previously learned, absorb at A280, but DNA has its maximum absorbance at 260. But DNA also has some absorbance at 280. So you're going to expect to see a higher absorbance at 260 than 280, but you should have absorbances at both wavelengths. Your 260 divided by 280 ratio ideally should be 1.8 if you have pure DNA. If it is higher, 2.0, that means you have some RNA contamination. You might have, when you were extracting your band with the needle, maybe you had your needle too low and you brought in some of that RNA, for example. If your ratio, 260 divided by 280, is around 1.6, this means you have protein contamination. So this is caused by, remember, protein absorbs at 280. So if you have a higher 280, that's going to decrease your ratio, and that's why it tells you you have protein contamination in there. So remember, the upper band is protein. So if you've got some of that in there, then this might affect your ratio there. But if you have pure DNA, it's a ratio of approximately 1.8. So this is how you're measuring the purity of your DNA. Now you also want to be able to measure the yield of your DNA. And you're going to take the number that you get for your 260, the absorbance at 260, and you need to multiply it by the dilution factor to be able to get back to the original concentration that you had in the tube. But neither of these have units. You want to relate it to a constant, and the constant can be, for DNA, 50 micrograms per mil, for RNA, 40 micrograms per mil. If you are measuring oligonucleotides using this procedure, the constant will range between 20 to 40 micrograms per mil. And actually, when you order oligonucleotides, there's usually a little spec sheet that comes with it that will tell you what absorbance ratio to use. So these numbers come from, you have one absorbance unit of DNA. One absorbance unit of DNA is a concentration, for example, of 50 micrograms per mil. So that's where that number comes from. It relates the absorbance to the concentration. So now you have units in here, but you now have it in micrograms. You want to get it to a more usable number, so you're going to divide by 1,000 micrograms per milligram, and then your numbers will be in units of mg per mil. If you have brought up your DNA in 1 mil after you precipitated it, then makes the math easy. Mgs per mil times mils, this would just be 1. So is going to give you, if you look at the units, milligrams, and that's your yield of DNA. So you have your concentration, which is mgs per mil, you have your yield. Now remember, you don't always have to bring it up in 1 mil. As I said in lab, we bring it up in 0.5 mils. So in that case, this number would be 0.5 instead of 1. So that's why you always have to remember what volume you brought your DNA up in to dissolve it, so that you can accurately calculate your yield. So for your report, you're generally going to be asked to evaluate the purity, the concentration, and the yield on your DNA.